To answer that, we need to introduce isotopes. Many elements have isotopes. These are different varieties of an element with the same number of protons, but different number of neutrons in the nucleus. In some cases, one isotope is more common than others, but they are all isotopes of each other. Like how people of different races all belong to one human family, isotopes are like members of one elemental family. In some cases, one isotope is more common than others. We call it abundance. For example, the element of chlorine exists as two isotopes, chlorine-35 and chlorine-37. 35 is more abundant than 37, in that in all the chlorine atoms in the world, 77.5% of them are chlorine-35, and the rest are 37. Now, therefore, to say the relative atomic mass of chlorine is 35 or 37 would be a misrepresentation. We need to give each isotope a fair weighting when we calculate the relative atomic mass for the whole family. So we invite the idea of a weighted average from mathematics. In the example of chlorine, we must know the isotopic mass of each isotopes in question. Here, that would be 35 and 37. And the overall relative atomic mass would be 77.5% of 35 plus 22.5% of 37. Adding together will be around 35.45. Now, here is another example using silver. Silver also has two naturally occurring isotopes. Their isotopic masses are given in question with their respective abundance. Therefore, the calculation goes each of the isotopic mass times their respective abundance. We can always expect that the final answer to be lighter than the heaviest isotope, but heavier than the lightest member of the family. Sometimes the information would also be given on a mass spectra. We will talk about the technique later on. Here, all we need to know is how to read a mass spec and calculate relative atomic mass. Now, on the mass spec, the x-axis gives the isotopic mass number, and the y-axis gives the percentage abundance. Therefore, the relative atomic mass calculated from the given spectra is their respective isotopic mass multiplied by their abundance. The principle of mass spec is based on bending of the magnetic field, very much like rolling a ball when bowling. Heavier balls require larger force to reach the goal. Isotopes with different masses will bend to different degrees when accelerated. The lighter isotopes in this case will not reach the detection chamber because there's simply too much force. And isotopes with the intended mass will fly the route and reach detection chamber. We can then reset the acceleration applied to catch the lighter isotopes. Properties of isotopes. Chemical properties are dependent on the behavior of outer shell electrons. Since isotopes have the same outer shell arrangement, therefore, they tend to have similar chemical properties. Physical properties, however, are dependent more on the atomic mass. And because isotopes, some are heavier and some are lighter, then they tend to have different boiling or melting points. And that is due to intermolecular forces. We'll talk about that later in details.